So tonight we're gonna do anomaly detection. It's gonna be kind of like an overview and just 3 different methods that I worked with, and I was kind of working on a project and trying different ways to approach this anomaly detection. And this is part of the research I've done for that specific project. Again, like I mentioned earlier, data is coming from Sergio, and this is basically time series data for sensors that are able to just kind of like every 5 minutes are taking voltage data. So what if you look at this time series, I have kind of like filtered and kept only 4 different time series to see kind of like the first 2 ones at the top are pretty normal on a kind of like on a regular day, and these other 2 below, they have this drop in voltage. And one of the things that I was trying to do is to figure it out ways to isolate these points, right? How would I isolate this kind of drops in voltage that are not really huge, but in the same time are significant enough? Because if you see here, voltage, it's kind of like at about 1% above where it should be at 100%, and it drops to about 9%. So it's a 3% drop in voltage, which it's significant in a way. It's just like it's something that you would want to catch and be aware of, right? So if you look throughout the day, normally you will have ups and downs, just kind of like throughout the night, it's voltage, it's pretty kind of like nice and calm. And then once day starts, you'll start seeing spikes and drops and spikes and drops due to usage on by kind of like different people and everything. So these are data from transformers, right? So that's what I was kind of trying to achieve, just isolating those outliers. And in order to do that, one of the first things that you would do, we just kind of go for statistical measures, right? So you're trying to find the mean, the median, and the mode of this time series. And the reason I can actually do it on a time series is because this time series should be pretty normal. It should be kind of like with no trends and not much kind of weirdness happening. So it should be pretty normally distributed overall, right? There is a little bit of difference between day and night, right? But overall, if you look at the one at the top here, it's pretty stable throughout the day, right? Even the second one, it's pretty stable. Even though it's a little bit more agitated, it's still kind of more stable, right? So that's why I'm kind of starting from the premise that the data is pretty close to a normally distributed data set. And one of the ways to approach this is kind of like looking at the mean, median, and mode. And once you kind of have those ones, you can actually run a histogram over the data, and that would give you, if you look here, when you run a histogram, you kind of see the distribution of one of these data sets, right? This is kind of the first one up at the top. So throughout the presentation, what I've done, I made sure that I run the code for all 4 data sets, so we can actually see the just how the code applies to each and every one of them, right? So I have the IDs here, and you'll be able to see when we're going through the codes exactly the data for that specific ID. So this the kind of like the calmest one is the 1051, and the next calm one is the 1083, and then these other ones are the 1063 and 1077. So those are the ones in the middle that in kind of like in the following sets, right? So just kind of like a quick reminder, the mean is the average of all the numbers. So you sum all the numbers and divide them by the number of the actual count of numbers, right, to get the mean. The median, it's the middle value of the numbers, right? So let's say if you look in here, we would have, let's take the green one, right? So we would have, let's say the max would be somewhere around here. It's at 1.022, and the minimum would be between 0.91, and the median would be pretty much the one found in the middle between min and max. And then the mode, it's the data that's most frequently found in the data set, right? So if you look here, you would expect that the median to be somewhere around 1.07, 1.06, or 1.07, somewhere in that range, right? As you have, this seems to be a value that's kind of more often. And in here, though, the problem is that we will have these drops. So in reality, we will have two different modes for this data set, but we'll see a little bit later, right? So the next ones, like I was saying, are the histograms and the kernel density estimation, the KDE graph, right? So if you're not familiar with the KDE graph, it's basically a smoothed histograms. And the way it's calculated is for each point, it kind of like adds a normal distribution, a Gaussian distribution for each point, and then it sums up the values of all the normal distributions for each point. So for each and every point. So let's say here at 3, you have the normal distribution for 1, 2, and 3 points. So you'd have this value, this height here, plus this height, plus this height. So hence you get the highest point, right? And in here, you're just basically limited by this height and the height right there. So basically, wherever you draw a vertical, you sum up the intersection with all the all the Gaussian graphs for each and every point. So that's basically it. It's nothing fancy. It just kind of looks scarier than it is. So this is the formula if you want to get into it, but it's just the beauty of it is SciPy has everything built in. And if you look at the code that we're kind of like going to talk about tonight, most of the stuff, it's about plotting more than anything, right? So the math behind it is actually pretty straightforward. The code is driven by SciPy and the stats modules. So these are the two modules that we're going to be using tonight. So like I was saying earlier, right, it's just right now I am plotting kind of like more information about this data, about this time series, right? So in this graph, I have the actual data points, and I have the mean and the max. So the max is in red, the mean is in green. Then I have the mean, the median, and the mode, right? That's why I wanted to talk a little bit about them in the beginning. So you'll see that the mean, median, and mode are very close to one another in this central area. So if you look at the values here, they're 1.075, 1.075, 1.076. So they're very, very tight together because, like I mentioned earlier, this time series, it's pretty normal and pretty calm. So there is no need for that separation, right? Versus if we look a little bit lower here at one of these values, you'll see that right now the mean drops below most of the points in this area. So the mean, it's away from kind of like the mean, it's away from where you'd expect it to be because of the outliers. So the mean of a data set is very easily influenced by the outliers in a data set. So that's why we're kind of looking at all these three central tendency measurements, right? So the median and mode would give us a better understanding of what should happen with this data set if the outliers would not be in there, right? So that's basically what I'm kind of trying to achieve here. And for the code, it's I have two functions. One that's to print the histogram. And for the histogram, I'm just kind of, well, I'm printing both the histogram and the KDE, right, in here, in that maximum point, which is going to be important a little bit later down the road. So for this one and for this other one, I'm just kind of printing all the statistical dimensions, statistical measurements, right? So for the histogram, I'm just originally calculating the Gaussian KDE. So and there is only one parameter that you would apply to it, to the Gaussian KDE, which is this bandwidth method. And that tells you how much should it spread out the Gaussian, the bell curves, basically, right? So the more you spread them out, the smoother the function is. And the tighter it is, the more peaks and valleys you have. So here you see I have it as 0.6. If you drop down to 0.3 and rerun the code, you'll see that all of a sudden it's a lot kind of tighter, right? And if I go to even lower, 0.1, it's going to be a lot more agitated, right? So this is one of the parameters that you need to find and work with for your specific data set. So for this specific data set, 0.5, 0.6 work pretty well. So this is just basically what I was kind of working with and figure it out for this specific data set, right? So then basically all I'm doing, I'm just kind of plotting it. And to plot the X and Y values, I'm just creating a linear space of 1,000 values between the minimum and the maximum in our normalized voltage data. And then just kind of like I'm using the density values that are coming in from the Gaussian function. So these are the parameters that would go into the printout, right? Then the next thing I'm doing, I'm just kind of finding the peaks. So the peaks are the highest value that would show up in this distribution, right? In this KDE graph. So there will be that little red point. And that's important because, like I mentioned earlier, if you look at these ones, the ones that have the drops, you'll end up seeing that we have two peaks. Distribution right now becomes a bimodal distribution. And that's one way for us to figure out the outliers, right? So we can consider the distribution with the highest peak as our kind of like core set of data, and the other peak would be the set of outliers. And we're able to do that. And by finding this straw point, which is kind of like the lowest point in between the two high points, we can figure out where would we split the data from, right? So where can we draw that line to split between the two distributions, right? The two modes. So that way, by drawing a line through this point, we're able to say that, hey, everything to the right of it, it's the normal data, and everything to the left, it's the outliers. Does everything make sense? It's if it doesn't make any sense, please stop me, interrupt me. It's just kind of like most of all our presentations are more of an interactive thing. So I would rather have it kind of like explain it while I'm still talking about it than do like questions at the end of the whole presentation. So yeah, so if you guys have any questions at any point in time, please stop me.
The description of the multimodal stuff makes sense. I don't want to derail you too much, but I don't remember what Gaussian distributed variables are used for.
So basically, what they're doing, they're just creating this normally distributed plot around each and every point, right? So that way, for each and every point along the x-axis, you can sum up the values of each and every one of those distributions. Because if you look at this distribution here, the first one, for point 1, it's a very smooth bell curve distribution, right? The moment you add another one here, right, everywhere you start kind of like drawing a vertical line, you can sum up the vertical of one distribution plus the vertical of the other distribution, the value, the y value for each and every point on that distribution. And when you sum them up, you'll generate the vertical point here on the KD curve. Does that make sense?
Yeah, it does. Thanks.
So it's basically, if you think of a histogram, for a histogram, you just bin them in little kind of like bins, basically, right? You just figure out how many of these points do you have within that specific bin, and you count them. But because of that, you have a discrete series of values, right, for each bin. By doing the normally distributed just kind of putting a Gaussian distribution around each and every one of those points, when you sum them up, all of a sudden, rather than having the binning, you're having a nice smooth curve. So it's just basically KDE, all it does, it smooths a histogram. That's pretty much it. So does that make sense?
Yeah, thanks.
Okay. So, right, okay. So now that we kind of have an understanding of that, and what I'm doing with it here is just like I was saying earlier. Now we have having the bimodal distribution. We have the highest peak is the one that drives the most of the data, and then the lowest peak is the one that just kind of like the outliers would be around, right? And the green dot, which is the throw between these two distributions, is the separator line that we can use to kind of like take the outliers away from, separate the outliers from the regular rest of the data, right? So again, this was the first set of data points. I'm going to zoom out a little bit so you can actually see it, where it's pretty nice and smooth and decently normally distributed. It's a little bit skewed, and but in the end, for the purposes of finding the outliers, it's a good approximation, right? And then for this second one, it's pretty clear. Once you do this, it's pretty clear which ones are the outliers, and you can see that at about 1 at 100%, if you draw a line at 100%, it separates them pretty well, right? Then for this other one, we kind of see the exact same thing, where again, if we're at about 970, so 970, let's say somewhere around here, you clearly are able to separate the data from the outliers. So it's a very good way of just basically separating these outliers. So, and this other one here, which was a little bit more varied, kind of has the same thing in depending on the value of the KDE, right? So 0.6 allows me to not have a throw in between, but if I would have actually dropped it a little bit, I could have had another peak in here, and then that would allow me to separate some of these as outliers, right? But in the end, I was looking for something that's a little bit more drastical. The separation is a little bit more drastic. So, okay. So going back to the mode versus the mean, because it's very important in the next step, right? I just wanted you guys to kind of like have a clear understanding of, you see how the mean, it's really affected by the outliers. So in this case, the mean is at 1.001, right? While the median and the mode are pretty tight together at 1.01, right? So there, it's a clear separation between the mean and the rest of the stuff. So, okay, knowing that, we can go into another way of doing it, which would be using the standard deviation and the z-score. Standard deviations basically is a measure that kind of gives you how far away the points are and how varied the points are, right? In a data set relative to kind of like the main one is the mean, right? That you calculate it against. So how far are the points away from the mean, right? Kind of pretty big formula, but it's nothing fancy about it. And all the kind of stats libraries have a way to do it. Pandas has it, NumPy has it, so it's very easy to calculate standard deviation and the z-score, right? And the z-score is indicating how many standard deviation is each element away from the mean, right? And in a normal distribution, you have basically the mean would be here at 0, right? And with one standard deviation to the left and the right should contain 68% of the data points, right? A 2 standard deviation, you should be at 95%, and a 3 standard deviation, you're at 99.7% of the data set. So usually everything that's outside the 3 standard deviations or the 3 sigma is considered an outlier, right? So that's another way for us to try to find those outliers. So we're using this, and we're going to try to just basically do the exact same thing. And in the code, basically, I am just going one by one. So I am using each ID to create a unique data frame, calculate the z-score as a column. I set my threshold for 3 times the standard deviation. So I am just kind of creating this outlier column that's greater than the threshold, where it kind of gives a value for greater than threshold. And then calculate the mean and the standard deviation. So very simple, very straightforward using pandas, right? Then again, like I was saying, most of the code, it's about plotting. So we're plotting all this data here, and you see right now with green, we have the mean, and then we have the standard deviation as a 1 standard deviation, right? And then I didn't plot in the second standard deviation. I went straight to the 3rd standard deviation just to kind of give you the full band. So anything that would be outside of these 2 bands, the bands of the 3 standard deviations, so plus minus 3 standard deviations, would be considered an outlier, right? So applying the same exact principle to the second data set, right, which clearly has some outliers, just because the mean is so offset from where it should be, from kind of like where the mode and the mode are. No, okay, I'm sorry. I'm just the median and the mode. I could not think of the name, sorry. So because the mean is so offset, right? Right now, everything falls within 3 standard deviations, and it shows like we do not have any outliers. And that's the case for those ones. So in order to kind of get this, to find these outliers, we would need to actually reduce that number, the 3, right? So if we go here, and instead of having 3, we're going to 2.5. Now, all of a sudden, we're starting to getting outliers because we're just kind of tightening up the bands. But as a standard rule in statistics, it's just kind of like that 3 is the proper number to use. So just by doing that, you're not 100% sure that you'll get the right results. Especially right now, it's very easy to see if you get the results or not when you're working on 3-4 data set. I mean, 3-4 values. Even if you have, let's say, 100, you can plot all 100 of them, and you can visually test your code. But the moment you start having tens of thousands of time series, all of a sudden you start not being able to just kind of visualize it, and you have to trust the code that it does what's supposed to do. So in order to do that, there is another way to measure, and it's called the mean absolute deviation, and it creates also another value that's called this robust z-score. And the whole principle behind it is, like I was saying here, right? You see how the mean it's offset from the rest, right? But what happens if you replace the mean with the mode or the median in the calculations for the standard deviation and finding the outliers and the z-score, right? So in case you just basically replace that mean with one of the other two values, you'll have you'll be less influenced by the outliers, and your bands are going to be more normal. So this is basically the whole principle behind the mean absolute deviation and the robust z-score. So the mean absolute deviation is a measure of variability that represents the average absolute difference between each data point and the mean of the data set. So it's basically still using the mean, but it's calculating the difference between each point to that mean. And it's kind of like one step into a two-step process, which is this robust z-score, which it's using this time the median rather than mean. Oops, sorry. So where are you? Okay, so it's using the median in the calculation rather than mean, and it's using the MAD as well, right? So median, the mean, it's still part of the calculation, but it's not as important, right? So just by doing this, all of a sudden, we're going to move our bands back to where they should actually be if the data would not have outliers. So that's pretty much the principle behind it. So for the robust z-score, again, you just calculate it through the formula, which is kind of like the each point in this v-norm column minus the median of the column, and it's an absolute value, and it finds the mean of it, and that's going to be the MAD. And then you're basically using the median value with the median, and then right now to create the bands, you're using a robust threshold, which is standard to be used at 3.5. Also, you see here for the robust score, there is this constant of 0.6745 that's used as a multiplier just to kind of like bring the values of this z-score in the same realm and the same sizes to the ones of the normal z-score, right? So this is just basically a scalar to bring the robust z-score in the same range with the other one, with the regular z-score, right? So in here, the same way, we're just kind of plotting it. And for this one, the median, you'll see it's pretty centered. And for this one, it wasn't a problem. So the mean and the median would be very close together. And in here, just because of the bands are a little tighter, we already find one of the outliers, right? We'll find that point as an outlier. And in here, again, now see how the median line, it's a lot more centered on most of the data. So it makes a lot more sense to have just kind of like when you have the bands, you clearly see the outliers, right? So this is basically the principle behind this robust score. So does this make any sense? Do you guys have any problem or any questions? I feel like I'm just kind of like running through the presentation, and just want to make sure that everybody gets an understanding of it.
Oh, this is great. Thank you.
Okay, perfect.
Yeah, Anton,
Yes.
one question.
Yes.
So what would happen if there were two similar drops in the
They will be
values?
caught as well. They will be caught outside, right? So it's
Yeah.
all that's going to happen basically is, let's say, best thing to visualize that would be here with the KD, right? So if you'd have two of them, it's basically almost like if you squish all these data points, if you squish them to the vertical axis, if you bring everything to the vertical axis, right, to the y-axis, you'll see that you have this group of points that represents the main, right, the main time series, and then the outliers are squished in this other part of the kind of like the y-axis here, right, between 0.92 and 0.96, right? So if you would have two of them, you would see if they're kind of like in the same range with this between 0.92 and 0.96, all they would do is just they would increase the height of this extra point here, right? And the distribution
There's
is
more points on that. Okay.
right. So there are more points in that area. So the histogram is going to be taller, and that point is going to move up as well, right? So the only time that this becomes a problem is when you have more outliers than you would have for what's it called, for your actual normal data. So in a day where you have mostly outliers, this whole thing would reverse, right? So that's something that you would need to catch specifically for at that point.
Because this is on a series by series basis. It doesn't compare one to the
right. This is series by series, right? So I'm just doing here series by series, and I'm just kind of like saying that, hey, for this series throughout this day, this is what happened. You can actually generalize it and have it on multiple series, and then from those multiple series to kind of like use your mode, for example, for all of them, and use that one as the starter point, or just the kind of like set up some specific parameter where you're expecting the data to be at, let's say, at 1 or 1.1 or 1.01, and just kind of like expect for that type of data and then choose on those. So those are things that you can manually do, right?
Okay, thank you.
Yeah. Okay. So basically, this is kind of doing it using the robustness score, the z-score, and the MAD, right? So that all of a sudden allows us to find these outliers, right? So the last one that I want to kind of go through is the DBSCAN algorithm. So the DBSCAN algorithm, it's a very interesting algorithm where basically it's looking for the density of points, and it has two parameters: epsilon, which is the distance between between the points when it's calculated, and the number of samples, right? So that's it. And unlike other kind of clustering algorithms, you don't have to tell it, hey, I need to split it in this many clusters, right? It will figure out on its own how many clusters does it need based on the epsilon and the minimum samples, right? So based on that distance and the minimum samples. So the way the algorithm works is just it chooses a point, then it kind of like draws a, we're talking right now in like a 2D kind of space, right? To make it easy to understand. So chooses a point, right? Then around each and every one of those points, it will draw a circle with a radius of epsilon, right? And then the other parameter was the minimum samples. So, and it looks within that circle to see if there are any other data points. If there are more than the minimum samples chosen, kind of like given in the as a parameter, then those points become part of that cluster. And for each and every one of those points, does the same thing. creates the circle, looks for samples in it, and just keeps on doing it until it finds no more points that would be within those kind of like circles of influence, right? And the moment it kind of runs out with a cluster, looks for another data point and tries again. And until it runs through all the data point and figures out. So that's basically what this one does. And once it figures out exactly all these points, it just basically brings them to clusters. So depending on your parameters, so on the radius and the radius and the minimum samples that you want, it just can find one cluster to hundreds of clusters, right?
So if your epsilon were too small, you would end up with essentially no clustering at all. It'd just be kind of evenly spread throughout the surface. And if your
Yes.
epsilon was too big, you'd end up with just one big cluster. Okay.
Right. Yes. So it's just that's the part. And in a way, that's kind of like the beauty of it, because for my specific data set, all I cared was about 2 clusters, right? So I'm looking, hey, based on this epsilon and the minimum samples, will you find for the first one and the last one, will you find one cluster? And for the ones in between that have the bimodal distribution, will you be able to find 2 clusters, right? So that was my whole train of thought. And I think this is a very simple. Yes.
Oh, sorry. What would be the axis in this chart here?
What do you mean?
What are the meaning of the feature 1 and feature 2 axis?
Oh, whatever it is, X and Y, whatever you have your data into, you know. It's
But in
just
this
like,
case, we remove the time, so we have the magnitude, and what will be the other?
well, yes, this can be time. Well, we'll talk about it because that's a gotcha, right? So we'll talk about it in a little bit. But basically, yes, in a 2D space, right now, think of this as latitude and longitude points, right? And those are actual
right.
points.
Yeah.
Very simple 2D, right? But for the case of the voltages here, the moment you have 2 dimensions, it's actually going to give you errors, because all you care about is just the voltage. So you need to do on a 1 dimension, right? So I'll talk about it in a second. So basically, this is all there is about this algorithm. It's very simple, but very, very powerful. It's just quite amazing. And the other beauty about the other beautiful thing about it is that it works in however many dimensions you want. It doesn't care. And the way it's written, the way it's implemented, it's very easy to just basically give it a matrix. So a NumPy array or a NumPy array of arrays, depending on how many dimensions do you want. And you just kind of pass the data, and it's going to figure it out, and it's going to return you the clusters. So it's a very powerful, and it's a pretty fast algorithm as well, right? So and we'll talk a little bit about how to find the proper epsilon and the minimum samples parameters, right? So basically, this is it, right? So here, let's apply it to our data set. And what we're going to do, we're just going to use this, just basically convert the vnorm into an array, and then we add the index as the second column, right? So right now we have a two-dimensional array. And the moment I'm running it, you'll see all these clusters, but they don't make much sense, right? It's not clustered in any way that I would expect it to, because it's taking into consideration both X and Y values. I mean, it's doing a great job of finding all these clusters, but it's not able to find, to kind of like do a separation between these outliers that are at the bottom and the normal data set that's at the top. So that's because we're doing it in a 2-dimension. But from a 2-dimensional standpoint, it does an amazing job of finding all these clusters, right? Now, and again, you can see it in this one right here. It just like makes really no sense what's happening with the clusters in a 2-dimension. So right now, if we do a dimensionality reduction, rather than passing like we're doing here, where we're having the x and the index, right, as a two axes, we're just passing only one axis, right, which is the one that we were using in the beginning, right? And when we run it, right now I'm just kind of running it specifically with an epsilon of 0.1, so it finds a ton of clusters, right? And the minimum samples of 10, so it kind of finds a lot of stuff around. And if you see, it's almost like it finds horizontal bands for this data, which is exactly what's happening, because right now the data is in its mind, it's all squished on the y-axis. So it's looking only along the y-axis and finds clusters based on only the y-axis, right? So here, all of a sudden, for this one, it finds a better way of kind of separating it. Figure out that, hey, that's one big cluster. And then here, it kind of finds 3 different clusters, but it's still, well, actually cluster -1, those are, it considers outliers, the blue ones right here. So yes, so the way it represents the data, it has the clusters, and everything else that's a -1, it's considered an outlier, right? But for our purposes, we're just kind of looking to find 2 clusters and 0 outliers. So the same thing, right? And the best way I found to do this, and just kind of like kind of through research, is to just basically run a grid search. And it's a very simple grid search. You just change the values for the epsilon values and the minimum sample values between kind of like a range that you want and you care about. And you figure out exactly what's happening. So let's say for an epsilon of 0.1, with a minimum of 2 samples, we get 2 clusters. This is for the first data series, time series, that was kind of like the one that was the most closer to normally distributed, right? So in here, it kind of finds 2 clusters. Then here, for 0.1 and 9 samples, it finds 4 clusters with a decent amount of outliers. And just kind of like, you can see it, just kind of like what you're expecting. So for our purposes, we need something that has like a 1 cluster and 0 outliers. So something in this range and even something in this range, right? For this data set would work. So anywhere between 0.3 to 0.5 and samples between 6 and I think 9 or 8, right? So that would be something that would work for this data set to give the result that we care about. For the other time series, here we're looking again in this area. We have right now we need 2 clusters, right? Because we have the bimodal distribution for this one. We have the outliers, so we want to catch the 2 clusters. So again, we're between 0.3 and just kind of like 2 to 8 samples, right, to give us what we care about. And then again, we can go at 0.5 all the way to the end. The same here, where we care about 2 clusters in the 0.3, 0.5. So this one goes all the way to the end, that we could use any values there. And the same pretty much here, where we're back to 1 cluster. That's what we care, and 0 outliers. So from this, you can actually try to find, so if you have, let's say, 10,000 of these, you can run and the grid search over all the data set and try to find the ones that would work for pretty much all your data, right? So it's a little bit of overfitting, but if that's what you need, especially for this case, that might be the best way to go. So here I kind of chose an epsilon of 0.5 to a minimum samples of 5. And if I run it, you can see that the first one found everything in cluster 0, which is exactly what I wanted. Here it was able to clearly separate cluster 0 from cluster 1, right? And then again, for this one, the same way. cluster 0 to cluster 1, and for the last one, the same way it found it. So it's pretty straightforward to use and quite amazing on the results. So yeah, so that's pretty much what I had. So question.
Anton, what's the, when you're doing the grid search, where are you getting the desired number of clusters? So I understand you want to minimize outliers because you want the cleanest separation between your clusters. But like for the first time series, we knew from examining the original plot that, yeah, this is probably all going to fit in a single cluster. But is this always going to be driven by observing the data first and deciding, okay, for the first two, a single cluster is the best, and clearly in the third and fourth, we've got two different sets, and so there should be two clusters? Or is there an automated version of this?
Well, for this specific case, I was able to visually analyze the data, right? So I knew exactly what I needed. I knew that for the first one and the last one, I needed one cluster with 0 outliers. And for this other one, to have the separation that I wanted, was basically 2 clusters with 0 outliers, right? That was my specific need for this, right? If you have a larger data set, you can just basically start doing some sort of statistical analysis, run all these through, just basically run that grid search to all the data, and then with the data that you get from the what's it called, for the grid search, you can just basically run some sort of analysis on that to figure out exactly what you need. So like with all the data projects, the biggest thing is to have a clear understanding of the data, right? That's the biggest thing. Once you have a clear understanding of the data, then you can generate your hypothesis and you can generate your specific needs and use cases that you need to work on, right? But the biggest thing is to understand the data. Once you understand the data, you can derive everything else. So that's kind of like the principle. So here it was me choosing specifically for this data set, exactly I need kind of like the parameters that give me one cluster, 0 outliers for the first and last, and 2 clusters, 0 outliers for the middle ones, right? So that was just basically me.
So when you looked at this plot, if if data set 4 had one chunk where things went down, and then later on it had another chunk that things went up, then you would either want 3 clusters, or you could take an absolute value and say
Right.
that would reduce it down to 2 clusters, because all you care is how far away it is from the normal, as opposed to whether it's positive away or negative away.
Exactly.
Okay.
And the other thing that you can keep on doing with that is, like for these other ones, right? For all the statistical measures, I have an upper band and a lower band, right? That I'm looking for here, right? The plus 3 standard deviations, minus 3 standard deviations, right? The same here for this robust z-score, the same way, 3.5 times the MAD and 3.5 below, I mean minus MAD, right? So the same type thing you can do with the clusters. Now that you have the clusters, you can try to find their centroid and use that centroid as kind of like a way to separate them. So that's how I was saying, at this point in time, once you have this data, it's up to you to choose how do you want to work with it, you know? So And that's why you need to have an understanding, because maybe your data will never ever go up, right? It always drops, or the other way around. It will always go up, right? So just my examples here are specifically tailored for this time series that I have as an example. So they're not necessarily generalized, but it's not too hard to go from here and start kind of generalizing and adding different parameters for different use cases. So yeah. Anything else? Any other questions?
Yeah, Anton, just a thought. I would like from the user's perspective. Is different if these issues are in one chunk or in multiple smaller chunks, right? So I was wondering if there's something that can be done on the time axis, but not exactly, not about the actual time, but the correlation or something like that. No, if try to detect if these occurrences are in sequence together or not, or things the like.
Well,
I was wondering if there's any data.
So here, for example,
that could be applied to time, no?
Right, where was it? Did I change it? Where was my code? I had one that was showing very nice. Here, for example, right? So you have these ones that happen in time, and this is kind of like a X and Y, right? So it's a two-dimensional one. So basically, right now, knowing each cluster, you can figure it out for each cluster when it's the time start and the time end, right? So you can do analysis that way. You can start splitting this time series that way. And you can actually see that, hey, for this time series, for example, in the outlier chunk, in this cluster, it starts at one point and ends at this other point, but there is not much data from the other clusters that it's in there. So you'll kind of understand that drops. But again, these are unique cases that you need to figure out. So you can definitely do it that way as well. Or the other way is when you're just doing the normal time series analysis, where you have these outliers, you see clearly that from the timestamp of the first one to the timestamp of the last one, they're pretty much all of them outliers. So you can see that that whole chunk, it's an outlier, right? So it happened between this time and this time. So
right.
It's just go ahead.
No, sorry.
Yeah, so you can analyze it in different ways. It's just the biggest thing is understanding the data, understanding what to expect from it. Because again, like I was saying in the beginning, I'm expecting it to be semi-normal distributed, right? I'm expecting the voltage to stay pretty kind of constant throughout the day. So if you have, let's say, if you're working with a stock price, you're not expecting that to stay pretty normal. So you have to figure out a way to take the trend out of it and just kind of reduce it to something that's more normally distributed, and then be able to do an analysis like this. So again, it's just like the use case dictates what algorithms and what methods do you do. And but my whole point, the whole point of this presentation is that you're not stuck into only one way, right? You have three different methods that you can do, and they all work quite awesome for it, right? So the KDE graph that allows you to see the distributions and kind of like gives you the bimodal distribution. That's one way to deal with it. The other one was through kind of like the robust Z-score and the MAD. right? Give you a pretty good way to choose it. And also clustering. You can just figure out what your parameters are and just kind of cluster everything based on that. So, and it just, I mean, it depends on what type of data do you have and the data dimensionality and a lot of other things. So any other questions? Okay, well, if no more questions, then thank you so much, guys. Really appreciate everybody being here. And we'll take a break throughout the new year. So our next meeting is gonna be in the 3rd Thursday of January, right? So we usually are doing it twice a month, the 1st Thursday of the month and then the 3rd Thursday of the month. So at this point in time, just because of the New Year's and holidays, we're gonna move to 3rd Thursday of January. So happy holidays and happy New Year to everybody.